Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms, that is backtracking. So this is also one problem solving technique which is used to solve the problems based upon the brute force approach. So it's a problem solving technique which follows the brute force. Brute force approach. So what is meant by this brute force approach? So brute force approach means checking all the possibilities to get the solution. So brute force checking all possibilities. Checking all possibilities. For example, so imagine you are having one lock and you are having some 5 keys. So you don't know the exact key which opens the lock. So what we'll do usually, so we'll try with each and every key. So at some point of time, so the lock will be opened with only one key among those 5 keys. That approach, that means without having any knowledge, just applying all possibilities is called the brute force. And here the backtracking will work with the help of a brute force with some sort of additional technology will be used for this brute force to calculate, to solve the problem using the backtracking. So here the name itself indicates the backtracking means if the current position is not, if the current solution is not viable or is not proper, then immediately we can undo. That means we can backtrack to the previous point and we can go with the alternate path. Okay, so if the current solution, that means whatever the solution we have solved, right? If the solution is not suitable, then backtrack and choose alternate path. Okay, you can choose an alternate path. So mainly this algorithm is suitable whenever there is no time limit to find the solution for a problem. So this works well when there is no time limit. There is no time limit to find solution to a problem. Right? There is no time limit. Then only this particular backtracking will be possible. And here we'll be getting all feasible solutions. Here we'll find all feasible solutions. So we have studied about these feasible solutions, right? So one problem can have a lot of solutions, but based upon the constraints, we are supposed to select the optimal solution. So all possible solutions, we call them as a feasible solutions. So here we are supposed to find these feasible solutions. And the solution for a problem will be obtained step by step and incrementally using recursive calls. This is also most important. So here the solutions will be obtained by using recursive calls. So step by step solution will be taken as well as in the incremental fashion, so using the recursive calls, right? So the three possible categories where we are going to use this backtracking, right? So three categories where we use backtracking. So the first one, decision problems. And these are the problems so which will be worked with the help of a decisions, right? So all feasible solutions, a feasible solution can be considered as a decision problem. Okay, so this is a feasible solution. And the second one, optimization problems. Optimization problem. So we have studied about these optimization problems. That means we can have a lot of feasible solutions, but based upon the constraints given, we have to select the optimal, that means a best solution. So that is an optimization problem. So best or better solution. So the first one is a feasible solution, and that may not be an optimal. And coming to the second one, it is a best or a better solution, optimal solution. And the third one is enumeration problems. This is nothing but all feasible solutions, all possible solutions. So if you want to find all possible solutions for a particular problem, then also we are going to use this enumeration problems. That such type of problems we call it as a enumeration problems. And if you want to solve a problem and get the optimal solution, that is called as an optimization problems. And if you want to solve a problem to get a normal solution that may be optimal or may not be optimal, that is called as a decision problems. So this backtracking problem solving technique will be used to solve these kind of problems: decision problems, optimization problems, and enumeration problems. And in order to find this feasibility, feasible solutions, here we are going to find out the state space tree. This is most important. So what is a state space tree? So this is a tree with all possibilities. So we need to construct the tree. Tree means nothing but a path. Okay, a path with all possibilities. Either it may be a solutions or a non-solution, right? So path with all possibilities. A solution which gives a solution or non-solution. So everything will be constructed in this state space tree. So with the help of this one, we are going to find out the solutions. So initially the backtracking will start with an empty set. Okay, initially the backtracking will start with an empty set, and after finding one solution, that solution will be added here. So this is nothing but the solution plus solution 1. So if it is feasible, then it will be inserted into this set. So it will be getting it as a S1. And afterwards, again the second solution. So if second solution is added here, so if it is feasible, second solution is feasible, then S2 will be added into this particular set. Otherwise, it will be just discarded, right? So these are nothing but a possible solutions: S1, S2, S3, and so on, Sn. Let it be. All are different solutions for a single problem. So initial set is empty set. So if S1 is a feasible solution, so based upon our constraints, right? S1 will be inserted into a set. And if coming to the second solution, if it is not feasible, okay, if it is not feasible, it doesn't meet our constraints, then S2 can't be inserted here, so we can simply avoid this S2. Then S3, the next solution. If this solution is feasible, which obeys all the constraints given by the user, then S3 will also be added to the initial set. That means this set, right? So in such a way, only the feasible solutions will be added into this initial set, and the solutions which are not viable or not suitable, they will be discarded. Okay. Now let us see the algorithm, a simple algorithm, how the backtracking will be applied. Okay, simple algorithm. So step 1, only the 3 steps will be there. Step 1, if the current position is the desired output, if it is a desired output, then success. Okay. Step 2, and if it fails, so else, and again if current position is not further explored or generated, then it is failed. That means if the path is not extended, okay, if the path is stopped, that means a dead end, then obviously we can say it as a failed. And step 3, else, that means this condition is also failed. If the current position is not a dead end, then backtrack with alternate path, explore and repeat steps 1, 2, 3. So again we have to repeat the same process. So one is if the current path or current position is the solution, that means a desired output, then we can stop, it is success. And if the current position is not further explored, right? So we are talking about the state space tree, right? So initial state, for example, it is A, B, C. Okay. Now, if it is a dead end, so we can say it is failed. If it is not dead end and it is again C, it is further explored, then we can backtrack and we can choose another path. Okay, so this is a way, and we can backtrack and we can go with the another path. And if it is here, then it is a dead end. It is not been explored further, right? But here there is an alternate way. If not C, we can move with the E. So in such cases we need to backtrack and explore with the another alternate path. So this is a simple algorithm. So that means if we reach to the dead end, okay, and if there is no further exploration, automatically we can stop. If there is an exploration, we can just backtrack and move with the alternate path. Now, what are the applications of this backtracking? So we'll see the applications. What are the different applications? Applications of backtracking. So by using this backtracking, we can solve the n queens problem. N queens problem. So in our further sessions, we are supposed to solve this one, right? So sum of subsets problem. Sum of subsets problem. Hamiltonian cycles or Hamiltonian paths. Finding Hamiltonian paths in a graph. Graph coloring problem. So etc. All these are the different applications where we are going to use this backtracking. Okay, so hope you understood the general method of this backtracking introduction. So what is exactly the backtracking? So it is similar to our dynamic programming, right? It is similar to our dynamic programming. In the dynamic programming also, we are supposed to find the optimization problems, right? Solve the optimization problems. And here also we are trying to find the optimization problems. But if our current path is not suitable, then again we can backtrack and we can choose the alternate path. So that is only one thing which is different from this backtracking and the dynamic programming, right? So let's stop here. Hope you understood this introduction about this backtracking. So in our further sessions, we will go with the applications, n queens and sum of subset problem, right? So let's stop here. So if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one application of backtracking, that is n queens problem. N queens problem. So first let us discuss about what is a problem exactly, and then we can see how to solve it by using the backtracking methodology. So in our previous session we have discussed about the introduction to backtracking. So how we can proceed for the backtracking. So that means getting all possible solutions by using the brute force approach, and if one solution is not viable or not suitable, then automatically we will backtrack and we'll choose the alternate path. And by means of a state space tree, we are going to solve the problems by using the backtracking. So state space tree is a tree which gives all the possible paths, including the solutions and non-soluted paths. So now let us see what is meant by this n queens problem. So arranging the queens in a checkboard or chessboard, right? So we know that in chess game we will be having a queen. So usually we call it as a mantri. So we know the steps that can be done by the queen. So the queen can move towards a row, a number of steps, towards a column, number of steps, and towards a diagonal way, number of steps, right? So here the problem is how we can arrange the number of queens in one chessboard so that there will be no attacking mode. That means no two queens should be in a same row, no two queens should be in a same column, and no two queens should be in the same diagonal path. So there should be no attacking mode, right? So n queens means arranging queens on a chessboard or a checkered board, right? Chessboard without attacking mode. So that means without attacking mode means no two queens should be in single row or a same row. Similarly, no two queens should be in a single column and no two queens should be in diagonal path. So if we arrange the queens, number of queens, let it be 4, 6 or 8, whatever it may be. So we have to arrange the queens on a board so that no two queens should be in a single row, no two queens should be in a single column, and no two queens should be in a diagonal path. So for this we have to consider the n by n boxes, a table with n by n columns or cells, we can say, right? For example, if you consider 4 queens, so we need to consider 4 rows and 4 columns, right? See, so we need to arrange the 4 queens in this board so that no two queens should be in the same row. For example, 4 queens are Q1, Q2, Q3, Q4. For example, if I arrange Q1 here, I can't arrange Q2 here or here or here, because the steps that can follow the queen is towards the rows, towards the columns, towards the diagonal. So number of steps, n number of steps, this queen can move this side or this side or this side. So where we can keep the queen 2, so you can arrange queen 2 here. Okay, so here also this queen can move this side, this way, and this way, right? So in such a way we have to arrange all the queens so that no two queens should be in a single row or a column or a diagonal path. For example, if queen 1 is here and if queen 2 is here, so that will be a diagonal path. So this is an attacking mode. Okay, so if Q2 is placed here, that is also attacking mode. And if Q2 is placed here, this will also be attacking mode, right? So we have to avoid all these things and we need to solve the problem. That means we have to arrange the queens, the number of queens on the board. For example, here we have considered 4, so we need to arrange the queens in 4 by 4 checkerboard. And if we consider 8 queens, so that should be arranged in 8 by 8 checkerboard or a chessboard. Similarly, if you consider 16 queens, so that should be arranged in 16 by 16 table. So without the attacking mode. So in general we are saying that it has a n queens problem, right? So now we will see the 4 by 4, right? In order to easy understanding and in order to solve the problem very easily. So let us consider 4, and by following the same procedure you can practice with 8 by 8 so that you will be getting it. Okay, now so for solving this one we are going to use the methodology called a backtracking. So here we can have a multiple solutions. So here now I am not talking about the optimal solution. So solution, it's a feasible solution. That means whatever it may be, the source will be, the element will be reaching to the destination. Okay, so it is not an optimal. I'm not talking about the optimal solution, best solution, right? So all the feasible solutions are the answers for this n queens by using the backtracking. So there will be a number of possibilities. So in order to, while solving that one, if it may not lead to the solution, it will backtrack and go with the another procedure, another path. So like that we have to solve the n queens problem, and so I'll show you for 4 queens problem, right? So let us take the 4 queens problem and let us solve it. So I will draw here. So I am taking 4 by 4 table. Okay, just now we have seen that we have to consider n by n table. So I am taking a 4 by 4 table. So 1, 2, 3, 4. Similarly 1, 2, 3 and 4. So these are the rows and these are the columns. And 4 queens, Q1, Q2, Q3, Q4, right? And now the problem becomes not n queens, it is 4 queens problem. Okay, now consider, so starting with the root, let us consider it as a root. So from root we can travel first here. I will go with so there are 4 columns, let it be 4 columns. If Q1 falls at first, okay, so that means place here Q1, then where the Q2 should be placed, so then let it be, if Q2 placed in 2, okay, because Q2 can't be placed in the first column. Okay, so just here you can see no 2 queens in row, column, diagonal. Right? Now, if you place a Q2, now we have placed a Q1 at the first position, right? So starting with the first column. Next, where we have to insert the Q2. So if Q2 is placed here, okay, what is the problem here? You can see both the queens will be in the same column, violate this one, right? So we should not place here. And if you place here, so here, and then also the Q1 and Q2, for example, I'll write here, okay? Now see, Q1 and Q2 both place in the same row, so we should not place here. Q1, you should not place here. Q1, what happens here? Here also we can't place because diagonal. What about here? Yes, there is no problem. So here you can see both Q1, Q2 are not in the same row, not in the same column, and not in the diagonal position. Yes. So here we are placing Q2. So Q1, Q2. Q1 in the first column, Q2 in the second column. Okay. Next. What about the Q3? Q3. So what about here? Q3. If you place Q3 here, what happens? Q2 and Q3 are diagonal, so we should not place here. What about the Q3 here? Again it's a diagonal, so we should not place here. What about the Q3 here? Yes. So we can't place Q3 here also because both in the same column, right? So this is a safe. So sorry, here also we can't place here, right? Q3 cannot also be placed here because Q1 and Q2 both equal, right? So see, there is no option for Q3 to place Q3. Hope you understood. So if you place Q3, it violates the same column. So if you place Q3 here, what happens? Diagonal. If you place Q3, again both are in the same column. And if you place Q3, diagonal. So there is no position to place Q3. So this path doesn't suit or doesn't give the proper solution. So backtrack. So here we can't place the Q3. Now go back. Go back. This is a backtracking. Go back and change the position of Q2. Change the position of Q2 because So if you place Q2 here, we can't place Q3 in the next one, right? Next step. So we need to backtrack and we need to change the Q2. So I'll change the Q2 here. So if I place Q2 here, diagonal, this is not possible. And if you place Q2, this is also not possible. So if I place Q2 here, yes, there will be no problem. Now the second path, Q2 in fourth position. So Q1 in first column, Q2 in fourth column. Yes. Now, so this is a backtrack. Okay, this is a backtrack. And now, what is the next step? Q3, where we have to place the Q3. So I'll write the boxes. Right? If you place Q3, again, both fall in the same column. So we should not place here. And if you place Q3, is there any problem here? No problem. So Q1, Q3 both are in a different rows and columns, and Q2, Q3 both are in different columns. There is no diagonal path, there is no column, there is no row. So Q3 can be placed in Q2, second one, right? So Q3 in the second one. Now, what about the Q4? Where we have to place the Q4? Again, I'll draw the same thing. So now we need to place the Q4, the last queen. Let us start with here. We can't place here, right? Because both fall in the same column. Here also both fall in the same column. There is only one position, Q4. There is only one position, that is the third position, right? So where we can place the Q4. But what happens? Again, Q3 and Q4 falls in the diagonal path. So this is also wrong place. And here we can't give the Q4 because again two queens will be in the same column. So this, if you place Q3 here, we can't place Q4 anywhere else. So it stops here. Again, backtrack. So we need to change the position of Q3. We need to change the position of Q3. So this is a backtracking, right? So it will be removed here. It should be removed here. Where we can place, there is no position here. So if you place a Q3 here, diagonal, in this position, there is no possible position to place the Q4. So this is also not correct position. And here also we can't do this. So again, go to backtrack. Right. So here we got the backtrack here. Again, there is no position. So backtrack to Q2. We need to change the position of Q2. So there is no possibility. If you place here, there is no possibility here. If you place here, already we have taken here. See, if you change the position of Q2 here, there is a diagonal, so we can't place here. If you place here, there is also violation of rule. So the only position is Q2, third position. Already we have done, but we are not getting the solution if you place Q2 in the third position. So again, backtrack. We need to change the position of Q1. So let us change the position of Q1 now. So move to the second one. Right? Then what about the position of Q2? So here we can't place diagonal, and in this position we can't place because both falls in the same column. Here also we can't place, and here we can place it. So Q2. Then what about a Q3? Okay, Q3. So there is only two possibilities, Q3 in this place and in this place. So Q3. What happens? See, so this is a diagonal, so we can't place here. What about here? Yes, we can place a Q3 here. There is no violation of rules because no other queen is available in the same row, same column and diagonal. So Q3 can be placed in first position, and from this we can go with the Q4. Now Q4. So only one option. If you place Q4, is there any problem here? So there is no problem. So you can observe no two queens fall in the same row or same column. Either in the diagonal. So there is no attacking mode here. So Q4 can be placed in 3 with a safe, without any attacking mode. So you got a solution here. So placing the Q1 in 2, placing the Q2 in 4, placing the Q3 in 1, and placing the Q4 in 3. So this becomes one possible solution. This becomes the one possible solution in order to place or arrange the 4 queens without any attacking mode. Right? So what happens here? So we have started from the first position. We have started from the first position and we have gone through, but there is no place of Q3 without any attacking mode. So we have taken the backtracking. We have taken the backtracking and we have changed the position of Q2. Sorry. So here we have backtracked this one. Okay, we have changed the backtrack here, right? So the backtrack will be this one, right? Backtrack. And similarly, we changed the Q2 position from third column to 4th column. And again we have started the procedure, but here we got a problem for Q4, arranging of Q4. So we have backtracked to Q3 and even we can change the position. We didn't get the location where we have to place the Q4. So again backtracked, and again we have changed the position of Q1. So what happens for finding the solution? If we are not getting the perfect solution, just we are backtracking and we are keep moving on to the next alternate path, alternate solution. Okay, so this is how we can solve the n queens problem. Okay, the same thing you can apply by using the state space tree. So this is not only the solution, there might be multiple solutions. Okay, there might be multiple solutions. For example, if you draw the state space tree for this one, see, one is a root. From this root, there are 4 possibilities. 4 possibilities. Q1, the first level is a Q1, placing of Q1. Okay. So if the Q1 is placed in a first column, second column, third column, and a 4th column. 4 possibilities. Okay. After that, from Q1 we can get 3 more paths. Q2. And from here also we can get 3 more paths. Q2. 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 From here also we can get 3 more paths. Q2. 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 And from here also we can get 4 more paths, 3 paths. That means, see, possibility. So if Q1 is at 1, position 1, in the second column, if you place Q2, third column, 4th column. Second, here the first column, second, third column, and 4th column. Here first column, second column, 4th column. First column, second column, third column. So all the possibilities. So 1 in Q1, 2 in Q2, 1 in Q1, 3 in Q2. So like that. And similarly, from here again we can have a Q3, and here also 2 possible things, Q3. See, this is the state space tree for a 4 queens. That means these are the lot of, all the possible paths. So some may have the possibility solutions, feasible solutions, and some may not have the feasible solutions, right? So previously we have gone through the directly backtracking method, and we found one solution, that is placing of Q1 in second column and placing of Q2 in 4th column, placing of Q3 in first column, and placing of Q4 in 3rd column will give the arrangement of queens without the attacking mode. But here you can see all the possible paths. So 1 in Q1, 2 in Q2, and 3 in Q3 and 4 in Q4. So we can check all the possibilities here, right? So let us check these possibilities. For example, consider this one by using the state space tree. How we can find out? See, first possible paths 1, 2, 3, 4. So placing Q1 at 1, placing 2 in a Q2, Q3, Q4. So this completely violates the rule because we have said that no two queens should be in the same row. But here all the 4 queens will be in the same row. But that is one possible path. So this is not valid, right? So this path is not a valid path. So we may not consider this one. We may not consider this one, right? Now, second possibility. What is the second possibility? So let us check the second possibility here also. So place a Q1 and 3 in Q2. See, 2 in Q2, sorry, Q3, okay, and 4 in Q4. So again it violates the rule, right? Diagonal. So this possibility is not possible, right? So this possibility is also not, this path is also not possible, right? So like that we can check each and every path here and we can find out the solution. So one solution, let us check one solution. So we found that 2. So Q1 in 2, right? So whatever the solution we found, just we will see Q1 in 2 and Q2 in 4, Q2 in 4, Q2 in 4 and then Q3 in 1. So Q3. So Q3 in 1 and similarly Q4 in 3. So this is a possible path. This is a possible path. So we will see one more possible path. So just a reflection 3, 1, 4, 2. Right? So let us check the reflection, mirroring, right? So placing Q1 in 3, Q1, Q2 in 1, Q2, Q3 in 4, sorry, Q3 in 4, next Q4 in 2. So this is also one possible solution. So here also we didn't get any attacking mode, right? So we have placed the queens so that there is no attacking mode for all the queens. Right? So like that, this is the complete, this graph is somewhat clumsy, please excuse me. So these are all the possible paths. Okay, how many ways we can arrange the 4 queens in this particular checkbox. And from this, so some may have the possible solution, feasible solutions, and some may not lead the solutions. So like this, we can find the possible solutions in a solution set. So here we are not talking about the feasible, optimal solution. So we are talking about just the feasible solutions. What are the feasible solutions, right? So this is a small example for solving the 4 queens problem. So just try the method for 8 queens problem to solve the 8 queens problem so that you will be better understand. Okay, you can better understand for that. So let's stop here. Hope you enjoyed the session. If you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more concept in backtracking, that is a sum of subsets problem. Sum of subset. So we know that a subset, right? So we'll take a set of elements, some x1, x2, x3 and so on, xn, and from this particular set we are supposed to find out the subsets, right? So all the combination of subsets, right? Let it be x1 comma x2 is one subset, x1 comma x3 is another subset, x1 x2, x3 are one subset, and similarly so on. There will be a lot of combinations, right? So here what we have to do is we need to consider a sum, right, which is denoted as m, and we need to form the subsets whose sum is equal to this m, right? For example, let us take 3, 4, 5, 2. So these are the elements in the set. Okay, these are the elements in the set. Now the total sum is 9. So we need to form the subsets where the sum of elements of that particular subset should be equal to 9. So here you can see 3, 4 and 2. So this is a subset of this main set whose sum is equal to 9. Similarly 4 comma 5. 4 comes before, no? So 4 comma 5. This is another subset whose sum is equal to given 9. If m is equal to 8, we need to form the subsets where sum of all the elements of subset must be equal to 8. So it will be 3 comma 5. Any other possibilities, any other solutions? No, there is no solution. So to find these subsets where sum is equal to given total is the problem of this sum of subset problem, and this will be implemented with the help of backtracking. So we have studied about the introduction of backtracking, and also we have seen one example of one application of backtracking, and here we are supposed to find the sum of subsets using a backtracking. So in this backtracking we are supposed to use the brute force. Brute force means checking all possibilities, right? And we need to find out the state space tree. So in this state space tree we will get all the combinations. So some paths may lead to the solution, some paths may not lead to the solution. So all the possible paths which may lead to solution and not solutions will be there in this state space tree. From there we will be getting the solutions, and here we are not finding the optimal solution, but we are finding all the feasible solutions. So here we can see this is not an optimal solution, because optimal solution is only one solution, best solution. So in this backtracking we are not finding the optimal solution, but we are finding all possible solutions. So in this one we can get the two possible solutions, right? Now we'll see the state space tree first, and then we'll write the step by step procedure, right? So we'll take the same example, and I'll draw the state space tree so that you will be getting the solutions, right? So let us consider it as W. So by observing this, you may having an idea about the 0-1 knapsack problem. So there also we are taking weights and a profit. So we need to consider the optimal solution by considering less number of weights with a more profit, right? So the same way here we are calling them as elements, and we are simply finding the sum of subsets. So the elements are 3, 4, 5 and 2, and m means a total which must be equal to 9. Yes. Now we are supposed to find the solution, state space tree, right? For example, consider them as x1, x2. So if x is equal to 0, that implies not consider. If x equal to 0, that implies not consider. If x equal to 1, it implies consider. So we need to check each and every possibility for all the elements with inclusion and without the inclusion. That means with consideration and without consideration, we need to find out the state space tree. Right? See, first let us take the sum as 0. Okay, right? 0 subset and weight is 9. Sum is 9. So this is the root. That means subset with 0 elements. Subset with 0 elements. Now, let us consider if you add one element, the first element, for example, let us consider only first element. What is the first element here? I will write here x1, x2, x3, x4. 4 elements are there. Consider x1. x1 is equal to 1. So if x is equal to 1, we are considering, right? So what is the first element? 3. So 3 will be added into this one, and from the weight we need to reduce the, from the sum we need to reduce the weight. What is the weight? 3. So 9 minus 3, it is 6. So we are considering two arguments. One is a subset, another one is a weight. Now check whether the sum of subset is equal to 9. No, right? So we can again further consider. See, x2 is equal to 1. Always this backtracking will be following the depth first search. Okay, this is most important. Always we need to find in a way that depth first search. So this element we need to find out this element. Now x2 is equal to 1. That means second element should be considered. So now the subset will be having 3, 4. And 4 will be reduced from 6. So it will be 2. Consider 3 plus 4, 7, which is not equal to 9. So it can be further down, right? Again depth first search. x3 is equal to 1. We can consider x3 also because the sum is less than 9, right? So x3 is 5. So here 3, 4, 5. 5 minus 2 minus 3. You can check the weight goes to the negative. So that implies the sum of subset is greater than the target value. So let it be, this is a target. Sum of subset is greater than the target. So we should not consider this one. So this is not a feasible, right? So not feasible. So what we have to do? We need to backtrack and move with the another direction. So backtrack towards this one and let us consider x3 is equal to 0. That means without considering x3. Without considering x3, so we are moving with 3, 4, 2. The same thing will be appear here. Again depth first search. Again you have to go with the depth first search. Now x4 is equal to 1. Okay, x4 is 2. Consider 3, 4, sorry, we have to consider 2 also. 2 and 2 minus 2, it is 0. You can say that sum of subset 3 plus 4 plus 2, it's 9, and also the target, the total value is 0. That means 9, right? So this is one solution. We got a solution, so we can stop here. And we need to find another possible solutions, right? So we need to find all the possibilities. So backtrack and consider if x4 is equal to 0, then it will be 3, 4, 2. What is the sum of subset? It is 7. So it can be further executed, right? Further evaluated, but it reaches to the last element. So not feasible. not feasible. So what we have to do, if it is not feasible, we need to backtrack. So move to the backtrack, and here again there is no position, so again backtrack, and again backtrack, and here you can consider x2 is equal to 0. So previously this path is considering x1, x2 0. Now the path, the elements are 3 and 6. From this again we need to find the depth first search. Consider x3 is equal to 1. Okay, depth first search means left side route. So x3, what is the third element? It is 5. Now 3 comma 5 1. So we need to reduce the weight from the target sum. So 3 plus 5, it is 8. Again still it is less than the target. It can again furtherly divided, right? x4 is equal to 1. So consider x4 3 5, x4 is 2, it is minus 1. You can check the total value, it becomes 10, which is greater than 9. So this is not feasible. This is not feasible. Backtrack, and possible position. x4 is equal to 0. Without considering x4, it will be 3 comma 5 1, and this cannot be further divided because x4 is the last element. So this is also not feasible. Again backtrack, this was completed, again backtrack, and here we can consider x3 is equal to 0. x3 equal to 0. x3 is equal to 0 means again we will get 3 6. So sum of subset 3, which is less than 9, further divided. So again x4 is equal to 1. So 3 comma 2 comma 4. What happens here? Sum of subset is 5. It can't be further divided because this is the last one. So this is not feasible. Similarly backtrack. So without considering x4 is equal to 0, this becomes again 3 comma 6. This is also not feasible. It can't be further divided because this is the last element. Now again backtrack. Check all the possibilities. No, here also there is no possibility. Backtrack, and again it moves to backtrack, and now we are supposed to consider x1 is equal to 0. So this complete path, these are all the possibilities when we consider x1 is equal to 1, and we need to consider the second one, that is x1 is equal to 0, right? So if x1 is equal to 0, the set will be again empty set with a 9, and we need to follow all the same things. So again consider x2 is equal to 1. What is x2? 4. 9 minus 4, it is 5. Sum of subset is less than 9. So further divided. x3 is equal to 1. Let it be 4 comma x3 is 5. Okay, and it will be 0. Right? What happens? 9. 9 becomes 9. So this is one solution. So I'll mark with a double circle, right? This is one more solution, and we need not move further. So backtrack for alternatives. Again x3 is equal to 0, not considering, so it will be 4 5. Again further can be divided, so x4 is equal to 1, 4 comma 2 comma 3. It can't further divided because x4 is the last element. So 4 plus 2, it says 6, not equal to 9. So this is not feasible. So backtrack, and check with the alternative. X4 is equal to 0, and it will be 4 comma 5, which is also not feasible. Now again move with the towards a backward, and here, and consider now x2 is equal to 0. x2 is equal to 0, right? Now what happens? Again empty set with 9. x3 is equal to 1. x3 is 5, 4. So 5, sum of subset is 5, which is less than 9. Further it can be divided. Consider x4 is equal to 1, 2. So then it will be 5 comma 2. So which is not further divided. So it is a not feasible. It's not a feasible. So move towards backtrack and consider x4 is equal to 0, and it will be again 5, 4, which is also not feasible. Right? Again backtrack, and now I'll write here, right? So consider x3 is equal to 0, x3 is equal to 0. x3 is equal to 0 means again it will becomes 9. So again it can be further divided. So x4 is equal to 1. So it becomes 2 comma 7. It's not feasible. Backtrack, again x4 is equal to 0. It will be blank and 9, which is not feasible. Right? So we are having only two possible solutions. One is 3, 4, 2 and 4 comma 5. Okay, manually we have seen all these things, right? Now the solutions will be, what are the solutions? How we can write down the solutions? So one is 3, 4, 2. 3, 4, 2, right? So this can be represented 3 comma 4 comma 2. This can be represented as 1, 1, 0, 1. 4 elements. We are considering the first element, second element, and we are not considering the third element, and we are considering the fourth element. So 3, 4, 7 plus fourth element 2, total becomes 9. Similarly, the second one, it is a 4 comma 5. So this can be represented as 0, 1, 1, 0. So this is not a binary. Okay, don't get confused. This is not a binary representation. So this represents which element should be considered and which element is not to be considered. Right? So again, this becomes 9. So these two are the solutions of sum of subset problem for a given example. Right? So what we are doing? So first we are starting with an empty set. We are inserting or adding one element to the empty set, and we are checking whether the sum of subset is equal to the target sum, and if it is not, or if it is less than, it can be further evaluated. That means again we can add one more element and we can check the total sum with the target sum. And if it is also not equal, if it is equal, then we can stop and we can consider that as a solution. And if it is not equal and it goes beyond the target, then obviously we have to stop and we have to backtrack and we have to select the alternate path. So in this state space tree, you can see we have considered all the possibilities. So some paths are not feasible. So you can check this path is not feasible, and this path is not feasible, this path is not feasible. So this state space tree will be having all the paths which leads to the feasible solutions and not feasible solutions. And backtracking is mainly to identify the multiple feasible solutions, not to the best or optimal solution. Right? So hope you understood this one, and practice with a more number of examples so that you can understand and you can get a complete clear-cut idea about this sum of subset problem using backtracking. So let's stop here. Hope you enjoyed the session. If you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more application in backtracking, that is finding Hamiltonian cycles in a graph. Hamiltonian cycles. So this is also one of the applications of backtracking. So backtracking main motto is to find all the feasible solutions, not the best solution, using backtracking. Okay, so we'll check all the possibilities, and if one possibility doesn't suitable, the solution doesn't suitable and it does not lead to the feasible solution, we are supposed to backtrack and we'll start with the alternate solution. Right, now coming to this particular Hamiltonian cycles, let us consider a graph. Okay, see, let us consider this graph. Let us consider this graph. So this graph means a combination of vertices and edges. Okay, so this is a graph, and this graph forms a cycle, right? So forms a cycle, and this graph will be having a lot of cycles. But here our main problem is finding of Hamiltonian cycles. So what is meant by Hamiltonian cycle? So consider a starting vertex, visit all other vertex at least once, exactly once, and come back to the original vertex from the source vertex. So this called as a Hamiltonian cycle. So I'll write what is a Hamiltonian cycle. Start from source vertex, visit all vertices exactly once, and come back to source vertex. This is called a Hamiltonian cycle. So we need to find out how many Hamiltonian cycles were there in this particular graph by using backtracking. Okay, so the same thing we have learned somewhere else, right? Yes. So the same problem, that means starting from source vertex, visiting all vertices exactly once, and coming back to the source vertex, is a solution of the traveling salesperson problem. But there we have to solve this with a minimum cost. That means the traveling salesperson have to start from the source vertex, visit all other vertices in the graph, and come back to the source vertex with a minimum cost. So there also will be getting a lot of cycles, lot of paths, but we are going to select only the optimal solution, right? But here we are finding all the possible paths. Okay, so this is a Hamiltonian cycles. So how we can find out these Hamiltonian cycles? See, let us start with the source. Let us consider this source. Don't change the source. So if you change the source, the cycle may be equal, right? So we should not consider that one. Fix it the source vertex and find out all possible paths, feasible solutions. So let it be. So first I will write the outgoing edges, okay, of every vertex. For example, consider A. So A is having outgoing vertices to B and C. B is having the outgoing vertices A, C, D. A, C and D. And C C is having outgoing vertex A, B and E. A, B and E. So it will be very easy. Okay. So D is having the outgoing vertices B, E, F. B, E, F. And E is having the outgoing vertex C, D, F. C, D, F. And F is having the outgoing vertices D and E. So with the help of this one, so usually we call it as an adjacency matrix. Okay, adjacency matrix. So instead of writing the adjacency matrix, I have written the complete nodes, adjacency nodes, right? Now start with the vertex, source vertex. So let it be my source vertex is A, right? A. So here we are starting from source vertex A and we have to visit all other vertices exactly once. So from A, what are the outgoing edges? B and C. Let it be. This is B and this is C. And we know that the backtracking will work on depth first search. So first we need to find out the depth. So yes, A and C. Now B, what are the outgoing edges? A, C and D. See, A, C and D. A is already visited because we are at B from A itself. So A is visited. So you need not consider A. So what are the outgoing edges? C and D. So C, D. Okay, C and D. Now we need to find out the depth. So C is A, B, E. So A, B were already visited. So if you are at C, we are from B. If you are in B, we are from A. So A, B are already visited. So only one vertex is not unvisited, that is E. So C is having E. Now check this E. E is having outgoing edges C, D, F. Among that, C is already visited. So there are only two possibilities, D and F. So D and F. Coming to D, B, E, F. So E is there, B is there. There is no F. So here we can have F. So F, D, E already visited, right? Now you can observe in this path A, B, C, E, D, F. So how many nodes are there? 1, 2, 3, 4, 5, 6 nodes are there. So you can see 1, 2, 3, 4, 5, 6. All nodes have been visited. So here the last step is F is the last node visited. So we need to check whether there is an edge between F and A. Then only it forms an Hamiltonian cycle. So start with the source vertex, visit all other nodes exactly once and come back to the source vertex. So start from the source vertex, visited all vertex exactly once, and now it have to visit back to source vertex. So F having edges D and E. So there is no direct connection from F to A. So this path is not feasible. So backtrack. So there is an alternate way. Okay, here from F there is D and E. In this path, check whether D and E have been visited or not. E is already visited, but D is not visited. So there is a path from F to D. Again check. So here you can see 1, 2, 3, 4, 5 and 6. So all nodes have been visited. And now it should go back to source vertex. So check whether D is having an edge to A. So D is having no edge to A. So this is also not feasible. So again backtrack. So here also one possibility, backtrack, and there is another possibility. So A, B and D. So from D, check B, E, F. B is already visited. So E and F. E and F. Now E. So depth first search, right? E. C, D, F. D is visited. So C and F. So here it will be C and it will be F. Coming to C, edges are A, B, E. Check out, A is there, B is there, E is there. So how many nodes we have visited here? 1, 2, 3, 4, 5. So this is not feasible because there is no edge from C. Okay, because C is having an edges towards A, B, E which are already visited. A, B, E in this path. So backtrack and follow this one. Okay. F. So from F there is an edge between D and E. So in this path A, B, D, E, F, check whether D and E are visited. Yes, D and E are visited. Now count the nodes. 1, 2, 3, 4, 5. So total nodes are 6. But only 5 are visited and there is no other edge which is used to visit the unvisited node. So this is also not feasible. Backtrack and go with the another possibility. So in order to reach F, we have to travel from A, B, D, F. So from F there is a D and E. So in this path D is already visited. We have to visit E. So there is one path. It is E. Now from E there is a C, D, F. Check. D, F are already visited. There is no edge to C here. So the next one is C. And you can check C, A, B, E. So A, B, E, all the three have been visited in this path. Now we have to check whether the 6 nodes have been visited. So 1, 2, 3, 4, 5, 6. Yes, all the nodes have been visited. So there might be a chance of having the Hamiltonian cycle. So there should be an edge from C to A. Then only we can say that is an Hamiltonian cycle. So check out C. A, B, E. So there is an edge towards A. So this is the one possible solution. So it forms a Hamiltonian cycle. And now go with the backtrack and move with the alternative. Next alternative, C. A, C. So C is having an edges from A, B, E. A is already visited. So there will be edges from B and E. Now B, depth for search. B is having edges towards A, C, D. A, C has already visited. So D. D, B, E, F. B is already visited. So E and F. E, C, D, F. C, D is already visited. F. F, D, E. D, E is already there. Now check the total number of nodes. 1, 2, 3, 4, 5, 6. So all nodes have been visited. So there is having a chance of getting the Hamiltonian cycle. So check out the edge from F to A. If there is an edge from F to A, then we can say this is a Hamiltonian cycle. So F didn't have the edge from F to A, right? So this is not feasible. Backtrack, go with the alternate solution F. So coming to F, D and E. So D is visited in this path, but E is not visited. So you can write it here, E. Now check E with C, D, F. C is there, D is there, F is there. So all nodes have been visited. So count the nodes. A, C, B, D, F, E. Total 6 nodes were there. So that implies there is a chance of getting Hamiltonian cycle. So we can say this is a Hamiltonian cycle if there is an edge between E and A. So E doesn't have an edge towards A. So this is also not feasible. This is not feasible. Now backtrack and here we are having an alternative. So E, A, C, E. E is having edges C, D, F. C is already visited. So we can have an edges towards D and F. Depth for search. So we need to find out the depth. D. D is having B, E, F. B, E, F. So in this path A, C, E, D, we are having only E. There is no path from B and F. So give the B here and F here. Coming to B. A, C, D. A is there, C is there, D is there. So not possible. So there is no new edge to unvisited nodes. So there is no, it's not a possible solution or a feasible solution. Move on to the backtrack towards this one and go with the alternative. F. F is having again D and E. So in this path A, C, E, D, F, we are having already D and E have been visited. See, E and D have been visited. So there is no edge towards the unvisited. So this is not a feasible solution. So backtrack and move with the alternative F. So F is having the edges D and E. So F is in this path A, C, E, F. There is no D. Okay, F is visited to D. Now you can check a D. B, E, F. In this path A, C, E, F, D. E, F are visited. B is not visited. So you can have B here. Now B. A, C, D. A is there, C is there, D is there. So all nodes visited, right? Now check the total number of nodes. 1, 2, 3, 4, 5, 6. So total nodes, all nodes have been visited exactly once. So it may lead to the Hamiltonian cycle. Now check the edge from B to A. Whether B is having an edge to A. Yes, it is having. So this forms the Hamiltonian cycle. This is one solution. Right? So all the possibilities we have compared and we got two Hamiltonian cycles for this particular graph. I'll write here the solutions. See, solutions, Hamiltonian solutions. The first solution is, see, A to B towards D towards F towards E and C and A. So this is the one Hamiltonian cycle. So starting from the source vertex, I am considering the source vertex as A. So starting from A, visiting B, D, F, E, C. That means all the remaining vertices exactly once and coming back to the A. So you can check here A to B. So this is one solution. A to B, B to D, D to F, F to E, E to C, C to A. So this is the solution 1. I'm just for representation, I am representing it as 1, just for understanding, right? This is the first solution. And the second solution, let us take this one. A to C, C to E, E to F, F to D, D to B, and B to A. So this is a one more solution. That is a one more Hamiltonian cycle. So let us draw the here. A to C, A to C, C to E, E to F, F to D, D to B, and B to A. So this is a second solution. Second solution, right? So in this particular graph, we are having two possible solutions. That means two Hamiltonian cycles. So starting from source vertex, visiting all vertices exactly once and reaching the source vertex is known as a Hamiltonian cycle, right? So here once again I am saying in this backtracking we are not finding the optimal solution. We are finding all the feasible solutions with the help of brute force approach. That means checking all possibilities. So for that we are drawing the state space tree where we can get all the feasible and non-feasible solutions. So this is a state space tree. Okay, from here we are able to find out all the feasible solutions. So here we got the feasible solutions, two solutions, right? So let's stop here. Hope you understood these Hamiltonian cycles, finding the Hamiltonian cycles in a graph, right? So if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we'll see one more application in backtracking, that is graph coloring problem. and we'll solve this graph coloring problem using a backtracking methodology. So imagine if you want to represent a map with different colors, so we need to take care that no two adjacent regions should be colored with the same color. So if that happens, so two different regions will be considered as a single region. So that we have to color a graph or color a map which is having a different regions with different colors without any overlapping, right? So similarly, let us take here a graph, and we need to color each and every node or vertex such that no two adjacent nodes or vertices should be colored with a similar color. See, let us take an example. There are 4 regions or 4 nodes. So these are the 4 nodes, and we need to color these 4 nodes with some 3 colors. So red, green and blue. Usually we call it as a RGB, right? Let us take the 3 colors. First, if we color the region A or node A with red, the adjacent node B should not be colored with red. So you can color it with green. And coming to the C, the third region, it should not be colored with green because it is adjacent. So it can be colored by using red or blue. Red or blue. And here, this should not be colored with a red because the adjacent region is filled with a red color. So it can be colored with green. Green, right? For example, let us take here, it has a red, okay? And here we can fill with a blue, right? So you can observe we have filled this one such that no adjacent nodes are colored with a similar color. See, A is colored with a red. What are the adjacents? So D and B. So both are with a different colors. And see, B is green. What are the adjacent? A and C. So A and C were not colored with a green. And C is red. What are the adjacents? D and B. Both are not colored with a red. And D, which is colored with a blue. So adjacent are A and C. A and C are not colored with a red. So this is one option. For example, if you consider here blue, if you color this region with a blue, then what happens here? D should not be colored with a blue or red because D is having adjacents A and C. A and C are colored with red and blue. So we should not color D with red and blue. It can be colored with a green. So this is another solution. So like that, we have to color all the regions with the different colors so that the no two adjacent nodes should be colored with a similar color. So for this, we are supposed to use the state space tree where we are having all possibilities, and from that we are finding the feasible solutions. And if one solution or one path may not lead to the feasible solution, there we are going to backtrack and select the alternate path. So like that, we have to solve the problem and we need to find multiple paths. That means the feasible solutions, right? Yes. Let us take the same example. I'll draw the example here. A, B, C, D. So these are the 4 regions. 4 regions or 4 nodes. So let us represent it as a 1. Okay. 1. In order to avoid the confusion, because we are also representing the colors with RGB. So in order to avoid the confusion, we can name it as 1, 2, 3, 4. Okay, 1, 2, 3, 4 are 4 nodes or 4 regions. And we need to color with red, green and blue. Red, green and blue. So root node, state space tree, first root node. From this root node, first we have to fill the node 1. So 1, 1, 1, right? And this one we are filling with red and green and blue. So 3. So we can fill the first region with either red, green or blue. So we need to write down all the possibilities, right? So I'll tell only this possibility, so you will be practicing with the remaining 2 possibilities, right? So first consider this one. If the, see, always the backtracking will work with the depth first search. So we need to solve it using depth first search, right? So 1, and from here there are 3 possibilities for filling the second node. See, these are the different nodes, or simply depth first search. So go with the x2 is equal to red. Okay, x2 is equal to red. If 1 is filled with red and R2 and node 2 is also filled with R, that means the 2 adjacent nodes comes with a similar color. So this is not a feasible solution. So we should not fill the second node with red. So backtrack, move with the alternatives. So there is a one more alternative, that x2 can be green, red and green. Is it possible? Yes. So 2 is an adjacent of 1 and 1 is filled with R. So 2 is not filled with R, 2 is filled with green. So this is possible way. Again, what is the next possibility? x3. That means the third region. Third region is red. Third region is red. Is it possible? Yes. So third region having a 2 adjacents, 4 and 2. 4 is not filled so far. 2 is filled with green. So 3 can fill with red. This is also possible. And again, fourth, x4 is equal to R. So x4 is equal to R. That means fourth region is filled with R. So is it proper? No, because 4 is having the adjacent nodes 1 and 3, and 1 and 3 nodes are filled with R. So we should not fill the 4 with R. So this fails. This is not a feasible solution. So backtrack and move with the next alternate path. That is, if x4 is filled with green, so x4 is filled with green. Is it possible? Yes. So 4 is having the adjacent nodes 1 and 3. So fourth region having the adjacent regions 1 and 3, both are filled with R. So 4 is filled with green. Yes, it's possible. So this will be one solution. So next possibility. If x4 is filled with blue, if x4 is filled with blue, that means a fourth region filled with blue. So this is also possible because adjacent nodes 1 and 3 filled with R, so 4 can be filled with blue. Yes, so this is second solution. Backtrack, move with the alternate. So 2 is filled with red and we have proceeded. Now, sorry, 3 is filled with red. Okay, now 3 is filled with green. Let us take 3 is filled with green, the next possibility, right? So is it feasible? No, because 3 is having the adjacent regions 4 and 2. 4 is not filled so far and 2 is filled with green. So 3 can't be filled with green. So this is not feasible. Similarly, move on with the next possibility. The third region filled with blue. We have to check. So third region is filled with blue. Okay. So is this may lead to the feasible solution? Let us check. 3 is having the 2 adjacent regions 4 and 2 and 4 not visited. 2 if is filled with green. So obviously 3 can be filled with blue. So this may lead to the feasible solution. Yes. So further depth first search. So we need to fill the fourth region. So let it be filled with red, R. So it may lead to feasible. So 4 is having adjacent regions 1 and 3. So 1 is filled with R. So 4 should not be filled with R. So this is not a feasible. Next, Next possibility, sorry, this is 4, right? So 4 is filled with green. Let us take 4 is filled with green and check whether it is a feasible. So 4 is having the adjacent regions 1 and 3, and 1 is filled with R, 3 is filled with blue. So obviously 4 can be filled with green. There is no overlapping. Yes, this is a third solution. And the next possibility, if the 4 is filled with blue, if the 4 is filled with blue, see, 4 is having the two adjacent nodes 1 and 3, 1 is filled with R, 3 is filled with blue, so 4 can't be filled with blue. So this is not possible. This is not possible, right? So again backtrack, and there is a one more possibility for 1. If x2 is filled with blue, see, the second node is filled with R, no solution. Second node filled with green, we got some 2 solutions, and now we are moving with second node filled with blue. So the next alternate is second is filled with blue. Okay. So x2 is equal to blue, and here x3 is equal to R. x3 is equal to R. Is it possible? So 3 is having, third region is having 2 adjacent nodes 4 and 2. 2 is filled with blue and 4 was not visited, so 3 can be filled with red. Yes, it is possible. Again, 4, x4 is equal to red. x4 is equal to red. So this is not possible because 4 is having adjacent nodes 3 and 1. Both are filled with red. So 4 can't be filled with red. So this is not possible. So backtrack and go with the alternate. x4 is equal to green. Now let us take green. Is it possible? See, 4 is having adjacent nodes 1 and 3. 1 and 3 both filled with R. So the fourth region can be filled with green. Yes. So this is one more solution. And what is the next alternative? If x4 is filled with blue, what happens? It may lead to feasible or not. So it is filled with blue. You can check for the adjacent nodes for 4 are 1 and 3. Both are filled with red. So 4 can be filled with blue. Yes. So this is one more solution. And we have completed this, all the 3 possibilities from region 3. Backtrack and move with the next possibility. If x3, that means the third region is filled with green. A third region filled with green. Is it possible? Yes, because 3 is having adjacent nodes 4 and 2. 4 is not visited, 2 is filled with blue. So 3 can be filled with green. Yes. Now x4 is equal to red. Is it possible? No, because 4 is having adjacent node 1 which is filled with R, so it can't be possible. So it is false. Again, G, that means a green. So if it is green, this is also not possible because 3 is adjacent to 4 which is filled with green. So 4 can't be filled with green. Next, blue. If this one is filled with blue, is it possible? Yes, because 4 is having adjacent nodes 1 and 3 which are filled with red and green. So it can be filled with blue. So this is one more solution. So here we have checked all the possibilities. Coming to the second node, only 2 possibilities we have checked. So again we have to go with the next possibility. That means if x3 is blue. So if it is blue, is it possible? See, 2 is an adjacent of 3 which is filled with blue, so this can't be happened. This can't be happened, right? So here we have checked with all possibilities, right? x3 is equal to blue, which is not possible. So we have checked all the possibilities here. Okay, these all possibilities have been fixed when the first node is fixed with R. First node is filled with R. So we have to repeat the same process and find out all the solutions if the first node is filled with green. And similarly, the next possibility if the first node is filled with blue. So there are three possibilities. The first node can be filled with either red or green or blue. So all these things we have done so far is if the first node is filled with red, right? So here the solutions 1, 2, 3, 4. So what is the first solution we got? This one. That means R, G, R, G. So R, G, R, G. This is the first solution. And the second solution, R, G, R, B. R, G, R, B. Third solution, R, G, B, G. R, G, B, G. And the next solution, R, B, R, G. R, B, R, G. Next solution, R, B, R, B. R, B, R, B. The next solution, R, B, G, B. R, B, G, B. So these are all the different solutions. Okay, these are all the different solutions. You can see, so without any overlapping, that means without filling the adjacent nodes with the similar color, so we can fill all the regions by using these combinations. If the first node is fixed with R, that means if it is filled with R. Similarly, we have to find out if the first node is filled with green, what are the possible solutions? And if the first node is filled with blue, what are the possible solutions? So I am just stopping here. You just practice with these two nodes, right? And solve this and comment all the possible solutions for this particular graph and all the possible solutions for all these possibilities, right? So hope you understood and enjoyed the session. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.